Okay, so yesterday we were discussing what makes theta fast, and one of the things that does is the aggregated signature gossip scheme, which is part of their consensus mechanism. So the whole, so we're going to talk about that today, and let's get started. So the whole idea is by aggregating the signatures as they go on, as you know, together in part, rather than a one-to-one, you can greatly reduce the number of messages that are sent in this multi-level consensus. So let's have a look. This is the official paper that goes into it. From the project, from the Theta project. And the key thing is, by using this mechanism, you can reduce the amount of communication, the amount of time it takes from a function of the number of nodes to a function of the log of the number of nodes. Now, if you don't, log is the concept of log, if you're not familiar, is the power that a number has to be raised to get the log number. So let's say log of base 10 of 100. Well, it would be 2 because 10 times 10 is 2. 1,000 would be 3. Or if you look at log of base 2, log of 4 of base 2 is 2 because 2 times 2 equals 4. That's the idea. So you're going from, let's say you're talking about base 2, you're going from 4, a function of the number, let's say number of nodes of 4, you're going to some function of 4 to some function of 2, or in the case of base 100, the function of 2, as opposed to, if you have 100 nodes, base 10, you would have, instead of taking 100, it would only be 2. And the base in this case is the number of neighbor nodes. So let's say you have a node. So what that means is the more neighbors, the more advantageous this is. So let's say you have 10 nodes around each node. So that means your base would be 10. So again, if you have 100 nodes in total, instead of taking a function of 100, it would take a function of 2. That's the secret sauce here, is the fact that it can reduce the time by doing aggregation. And here's the algorithm, and they go into all the mathematics in this paper and so on, and proofs and so on. But basically, L would be log of the number of nodes, number of neighbors, a base of number of neighbors to the number of nodes. So it would be, let's say, if you have 10 neighbors and you have 100 nodes, it would roughly take 2 iterations, because you would have the log of base 10 of 100. So what it does, it sends to the neighbors. If it's finalized, it's done. It gets the response, it verifies, and then it computes this aggregate and calculates how many signers we have. If it's greater than 2/3 of the nodes, you're done. So that's the whole concept of how this works, how this finalization works. Now they do get down here into some charts of some of their experimentation, and they looked at 1,000, 2,000, 3,000 guardian nodes. They looked at how many are bad. As you can see, there's none. How many max entries, how many messages. And obviously, if you have more bad nodes, more messages would need to be sent because it would take longer to achieve consensus. So this is where they talk about order. If you're not familiar, again, order is in computer science is basically how long something takes as a function of some input. So in this case, our input is nodes, and without this mechanism, it would be a function of the number of nodes. With it, it's a function of the log with the base of the number of neighbors, typical neighbors for the nodes, of the number of nodes. So you can see B is the average neighboring node of each guardian. Since each guardian has 20 or 30 neighbors, you can, this is how they do the calculations here, and you can put it in a scientific calculator and get the idea. But in essence, what they found is they would greatly reducing the number of messages. They were able to do things in roughly, even with these numbers of nodes, were able to do, I think, 5 iterations, they said. So, again, if you're interested in the details, this paper goes into great depth, and as you see, the more nodes, the greater the number of max entries, messages, and let's see, and the greater the percentage of bad nodes, the greater the number of messages. But what's interesting is if you have 1,000 nodes, you can have 20% bad nodes, and you don't get a huge increase in messages. It looks like, let's see, max entry. Well, that's interesting. So max entry in setting 4, well, you could take a look at it. Looks like it depends on the number of neighbor nodes. So that's what the different charts are: 20 neighbors, 30 neighbors, and this is for 20 neighbors. So you can see it kind of goes up and then goes up a lot. This one kind of stays the same until you get to about 20%. With 1,000 nodes, it's the same kind of thing. It really takes off if you have 30%. And this is if you have neighbors of 30 nodes. You need more than 20% bad nodes for the amount of messages to really shoot up. So hopefully this has given you a better idea of why Theta can be so fast by taking advantage of aggregation of the messages, aggregate valid signatures here. It can greatly speed up the process by greatly reducing the number of messages that need to be sent, especially if you have 20% or less bad nodes. So if this has been helpful to you, and I will include a link to this article in the in the notes if you are interested in looking at it yourself and getting into the details. But hopefully this has been helpful to you. If it has, please give a like And please ring the bell so that you can get notifications when you subscribe and get notifications. And I will speak to you next time.